Hello everyone, this is the video lecture for linear algebra for chapter 5, all of chapter 5. So we're going to start in 5.1, length and the dot product. Sorry for my handwriting, as always. Okay, length and dot product. There's a lot of different names for length in particular. So when they say length, they could also use the word norm. They can also use the word magnitude. Or just mag is another one. I've even heard mod, but I'm not going to go with that. That's not in the book. But I've heard that one as well. There's a lot of different names for this. But essentially, we also have the distance here. The length. I guess distance is another way for this. Which is essentially the Pythagorean theorem. And so I take each one of the elements in a vector and I square it, add them together, square root it. There you go. So the length of a vector, the magnitude of a vector, is the Pythagorean theorem. Pretty simple there. So there's one definition for you. Another one that we'll be seeing is unit vector. Unit vector. They often use U. U can mean all kind of different things, so don't think like U always means unit vector, because they'll be using U and V and W all over the place today. But that U does kind of relate to the unit vector sometimes, so they're using U specifically here because of unit vector, but it must be equal to, for the unit vector to be true, some vector V divided by its magnitude of that V. So that's V divided by the magnitude of V. You're dividing that vector by its distance. Okay. This results in a magnitude equal to 1. Magnitude equals 1. That's unit. Unit means 1. We've got distance between two vectors. Between two vectors. And again, I'm kind of giving you the notation that they use. Little d with a u and a v in there. But it's just the magnitude of u minus v. And you could also do v minus u. It doesn't really matter, because the Pythagorean theorem will keep them all positive anyways. So that's, again, Pythagorean theorem with that guy. And then finally, we're going to get to our dot product. Dot product is very, very important, and we'll be using it throughout this chapter. We got u dot v. Now I know it looks like multiply. We'll talk about it in here in a second. The formula is u1 v1 plus u2 v2 plus u3 v3 plus dot 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 for as long as you got elements of those vectors. So let me go ahead and show you a dot product example. So there's just a little example of what's going on here, and then I'll talk more about it. 1, 2, 3. Dot, and then the 4, 5, 6. They need to be the same size to make this thing work. So what I'm doing is I'm multiplying the first elements together, 1 times 4, and then plus, and then I got the 2 times the 5, and then plus, and I got the 3 times the 6. And so we get 4, 10, and 18 makes 32. There's your little example there on the dot product. So dot, often when you put a dot between two different things, it means to multiply. So in a way here, yes, we're multiplying two vectors, but I wouldn't just say multiply, because you're going to be seeing something here towards the end of this chapter where we're going to use multiply in a different way. So multiply kinda, but it just more of, like, I would say, instead of saying multiply, because we're going to be continuing on in linear algebra going a different way, let's think of it kind of like a formula. Okay, it's kind of like a formula. This is the basic way of seeing it. This is the more advanced way of seeing it. There's a formula that we apply to these two vectors, and notice that what happens is that we get these two vectors. They result in a scalar. That's super important. You're going from two vectors and you're making a scalar. So yeah, multiplying, but you're multiplying in a way to get a scalar. you're going to also have cross multiply here in a second, cross product, and that would be again a multiply in a way, but it will result in a vector. So there are differences here. Okay, sorry for talking too much about it. Let's keep going. So we got now the angle between two vectors, and it's more like a formula. We got cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. This is one very tricky formula to write down. It's a very simple formula to go and find. You find a dot product using this kind of formula, Pythagorean theorem on two vectors. You just have a big number here. You arc cosine to the other side, find theta, you're done. Very simple. But notice, like, you're multiplying these two, but remember, this is a number. That's a scalar. That's a scalar, and this is a scalar, like the whole thing. So you got this number times this number. Do you put a dot here? Well, I would if we were back in college algebra, maybe, but now we're in linear algebra. I'm going to say no, don't put a dot there because we already got a dot there. It's just kind of weird. Oh, well, should we put a time sign like that? No, because, again, there's a different kind of cross product that we'll be seeing there later as well. There's just nothing good to put there. If you really, really, really need something, you can put some parentheses, I guess, but that's just kind of bulky now. It's already got a lot of lines. And so another way that I've been taught with all this is, and this is going to be an interesting distinction here in a couple minutes, you can write these magnitudes of vectors with single lines. Now, I know that looks like absolute value, but you know it's not strictly absolute value because that's a vector inside. That way you know it's actually going to be a Pythagorean theorem. Let me give you an example here on the side. This is just on the side here. This is just Chad's little notes for you. So I got a vector 1, 2, let's say. And I want to find its magnitude, its distance. Well, I say, okay, the distance would then be 1 squared plus 2 squared. And so what? The square root of 5. There you go. Cool, we got it. But what if I had a vector, just, a little different vector. What if I had a vector of just 2? Just 2. Okay, well, I do the same thing, right? But I got the one number to do it. Well, the square and the square root cancel one another, and you get 2 out of it. Kind of interesting there, right? Okay, let's try one more. Let's say I had a negative 3. I want to find that distance. What's the distance for this guy? Well, as you kind of guessed, square root and square cancel, but remember that these are 2 negatives. Make a positive. You're going to result in a positive 3. So what happened from here to there? Isn't that kind of the absolute value in a way? Right? So when you're dealing with a single number, this distance, this Pythagorean theorem, actually does yield the absolute value. If you have a bigger dimension than just 1, then your same Pythagorean theorem, your absolute value, will always yield a positive number anyways. Kind of interesting there. So having single lines indicating absolute value is not wrong. You are actually doing that same process, you're just in a higher dimension. So there you go. Kind of some cool learning there. The thing is that I want to still make a distinction between absolute value. I'm not going to do it this way. Absolute value and magnitude, because the very next formula or theorem or whatever is the Cauchy-Schwarz. Sorry, I thought there was a T in there. Inequality. And this kind of like couples the two together. So here we go. I got the absolute value of the dot product is always less than or equal to the magnitudes or the distances of the vectors multiplied. Notice here, this is very interesting. We got a multiply, and we basically have another multiply right there, right? We got lines, we got lines. We got a U, we got a V. Same thing. So what's going on here? Well, this right here is definitely the absolute value. 100% for sure. Do you know why? Because the inside is a scalar. That dot product results in a scalar. So you're basically saying, what's the absolute value of negative 8? I mean, there's no vector inside. It's a number inside, just a number, and then you're doing this absolute value thing, okay? So you will always result in a positive number there. These guys are the magnitudes, again, kind of like absolute value, But then these are positive, and positive times a positive is still a positive. And so you can kind of see their relationship there. Okay, it's very interesting and similar. But again, I'm not going to go and prove it. I'm just showing you what they have in the book. Okay. Some more. We got U and V are orthogonal, and this will be very important here in a little bit. Orthogonal. Ortho is, I'm pretty sure it's Latin or Greek for like correct or right, like straight. And so we're making them straight. If you know the symbol for orthogonal, it looks kind of like that. You got a straight line on a plane right there. So orthogonal. When we got U dot V equals 0. Now notice again, this is U dot V equals 0 scalar. Okay, that's a scalar. So if I do a dot product, then they're orthogonal to one another. Okay, and orthogonal, again, just here's an example. We've got this vector here. This is U vector. This is a V vector here. And notice that they got a 90-degree angle. Couldn't you also go back to this formula here and discover if theta equals 90 degrees, then it's orthogonal? You see what I mean? It's just another way to do it. I'm not going to go and do that, but that's another way to do it. Orthogonal to one another. There you go. 90 degrees. Last one we have is triangular inequality. Triangular inequality. It's a very famous one. You use this in other classes as well, advanced math classes. U plus V, and then the magnitude of that, is always less than the magnitudes added separately. Okay. I know my handwriting's not perfect. Okay, so we got the magnitude of U plus V is always less than or equal to the magnitudes of them separated and then added. Here's an example I want to show you graphically. Let's say that I had a U vector and then a V vector following it. So this distance right here, that's U plus V. Notice that what you just found is that U plus the V, like this distance here, plus this distance here, is the distance total, right? So that's when they're equal to one another. But what if instead I had a U and a V, but right down here, this guy, that's my U plus V on the bottom there. This little dashed line down here. So I have this distance here. I don't know, let's call it 5. I got this distance here. Let's call this another 5. But here, this is not 10 anymore. It's not like you're going 10 distance there on the bottom. I don't know, maybe it's 7 or something. But, well, it's actually, just to be straight with you, it's 5 square root 2. So whatever it is, though, I'm just saying that you would have some kind of a distance here. No, it's not 5 square root 2. It's 5 divided by square root 2, I think. Yeah, something like that. Okay, I'm pretty sure. Something like that. Regardless, there's a different kind of number, and it's less. You can obviously see it's less than that. Yeah, it can't be 5 times the square root 2. It probably divide by square root 2. Blah, blah, blah. There you go graphically. So, let's do another, let's do an example or problem or whatever. Proofy stuff. So, 5183. Prove that if U is orthogonal to V and W, so it's orthogonal to both, because like you can put parentheses to kind of just make sure you see U is orthogonal to V and U is orthogonal to W, then U is orthogonal to CV plus DW for all C and D element of the reals. So what they're kind of saying is, I know that they're orthogonal to each one of these separately. So now, is U still orthogonal to this big old thing together? Okay, so this was separate. I guess you can say, like, let me write it out more correctly here. So let U, V, W element of Rn, so they're vectors such that U perpendicular to V and U perpendicular to W. So I think that's a little bit more clear than what I had written there, but regardless, there you go. So I'm perpendicular here, perpendicular here. Now are they perpendicular when you put them all together? So When I have these perpendiculars here, I'm going to say thus my u dot v is equal to 0. I think we had talked about that above. And u dot w is equal to 0. And those are scalars. So because they're perpendicular, my dot product is equal to 0. So let me start with this big old hunk of stuff right there. I got u dot, and then I got cv plus dw. I guess you could just, they already defined C and D is good enough for right now. So we got this. And I'm going to go ahead and simplify it a little bit. So what I want to do is actually do 2 steps. I'm going to distribute my dot product. Now this is one of those properties back in the book. I don't think I listed it here, but there is properties for this kind of stuff. I got then u dot cv plus u dot dw. And I'm going to keep on doing some of my properties here. That C can come to the front. Again, these are all just properties of the dot products listed in the book. Okay, hold on. I was trying to do a dot there. And then I'm going to distribute out the D. Well, it's not even distribute. It's kind of just move it out to the front. Okay. But it's interesting because we already said that u dot v and u dot w are equal to 0. Notice that. So I'm going to say, well, that's just a 0. And that's just a 0. And 0 times anything is 0. 0 plus 0 is 0, so 0. What I got here is that the dot product of these two is equal to 0. Therefore, 3 dots. Therefore, u is perpendicular to cv plus dw. And we're done. Okay. Next section, 5.2, inner product spaces. Inner product spaces. Okay. So we already saw the dot product, and we'll be continuing to use that as we keep going. That's my u dot v here. Okay. An inner product is very, very similar. They write it like this, and I gotta say, I think I used this on the quiz maybe 1 or 2 times. They make a very big deal about it in the book, and that's good. There is a distinction between them, but I'm going to say when you are thinking about what an inner product is, when you see little alligators and stuff like that, just think of it like dot product. Think of them like the same thing. I know they're not exactly the same thing. I'm going to show you there's a difference, but they're almost so similar that I wouldn't consider something different, okay? So they're almost the same. The difference is that my inner product can be redefined. It can be, I like to say redefined. But it's really just defined. With a formula of some kind, okay? And so there's obviously some different styles that are possible, but let me just make up one here real quick if that's okay. I'm just going to make one up. So if I were to do this inner product, let's just say that it was always a 2 u1v1 plus 3 u2v2 plus ... I don't know, something like that. Notice that these 2's and 3's are not the same as the dot product. The dot product does not have a 2 and a 3 there. The dot product is this stuff. That's my dot product right there. But there's additional changes to it. And so that's what an inner product is. It could be a little extra. Okay, redefined a little bit. But still, again, very similar to how a dot product is. And almost always is going to be the same whenever you do like proofs and whatnot. Okay, so just think that way. Both of these result in a scalar. Okay, that's a big one. Result in a scalar. Again, just a number of some kind. So let me give you some definitions. These are not properties, apparently. These are definitions of an inner product. Okay? We will use these here in just a second. So these are definitions. All inner products must have u v equal to v u. So they're commutative. Okay? U, and then v plus w should also equal u plus v. I'm sorry, not u plus v. uv plus uw. So that's the distributive rule. We've got c uv should equal cu v. That's the associative. Pretty sure. Yeah, I think that's associative. And then finally we got, and this is kind of tied into two of them, into this one little property. So bear with me. This is going to be the inner product of v and v should be greater than or equal to 0, scalar, okay, and then comma, big comma there, and also vv equals 0 if and only if, again, if and only if is kind of special, okay? That's why it's got the two f's there. It's not a typo. My v vector is equal to the 0 vector. Okay, so 1, 2, 3, 4 definitions for this inner product stuff. We're going to be using that here in just a second. So let me give you one last thing from this section, and then we'll be doing this stuff here. Okay, so there's this last thing called a projection of u vector onto v vector. Now, whenever I've seen in different books where they flip these v's and u's and stuff like that, so however you want to, memorize it, but let me give you what this looks like. Projection of u onto v. See, I even stumble on this stuff. Notice that it's not sequential in English. It's projection of u onto v. Okay, so v's the little guy. Because I'm just trying to have ways for you can kind of remember this. You're doing the projection of u. Okay, you're doing the projection of u. Projection of u. Okay, cool. But it's onto v. So in case someone's asked, where are you putting this projection on the v? A projection is actually pretty neat. Let me just go ahead and change my color back here. Let me give you the formula real quick, and then we'll talk about the projections just a tiny bit here. So u, v, inner product. Again, you can use dot product in place of this, and it's the same thing. And then with a v vector there. Notice that we got u, v, 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 v. And this still results in a vector, okay? Remember, see how there's a big scalar right here times a vector makes a vector. Okay, cool. So just real quick, let's say I have a u right here, and let's say I have a v right here, and your u is projected on 90 degrees right here. This is your projection vector right there. I'm not going to write the whole thing, just there you go. I like to think of it kind of like a shadow. So like you had the sun up here, and what would the shadow of that u be on the v vector? Of course, it doesn't have to be perfectly lined there, but I'm saying it has to be the 90 degrees from your v, okay? So that's a projection. It's this guy right here. This is your projection. In fact, let me just color it one more time just so you can see. This is that projection vector right there. This guy. That's this result. It's a vector. It's a tinier vector. Notice also it's a scalar of v. It's on v. It's literally on v somehow, but it's just, and it's parallel to v, but it's a scalar of that, okay? Cool. Okay, sorry if I was talking too much about it. Let's keep going. So, this is kind of a proof. It does say prove in the front, so prove that this function is an inner product, or results in an inner product space in V. I just want to see, does this thing make an inner product? Does it work? Okay, so UV, again, we're redefining it as C1 U1 V1 plus C2 U2 V2 plus ... all the way out to N. And they're saying specifically that all my CIs, all my C's, are going to be greater than 0. That's their language. I would probably put like for all I or for all CI or something like that. Cool. Does this make a true inner product? Is this a good formula? Like, what if I put squares right here and here? Does that still work? That's kind of the point that we're getting at. So how do I prove that one of these inner products works or not? Does this formula hold? And so I'm going to go back to my four definitions and see if this works. Okay. So first off, I want to see if UV is equal to VU. Now, you don't have to write this, but that's just a reminder for me to say, this is what I want. So I'm going to start with VU and go backwards if that's okay. And so then that would be a C1 V1 U1 plus C2 V2 U2 plus ... And so I can rewrite it because scalars are associative. They're commutative across multiplication. So we can rewrite it with the U's first and then the V's. And, well, we already defined this one as UV. So that one's done. I don't know if you want to put a little box there or a little happy face that you're done with that one, but it's good enough. Keep going. The happy face is not professional. Just going to say that. But it would be funny to see. So number 2, I want this one here to distribute. Looks like that. So that's just my reminder. I'm going to start with this guy and figure out how to get to the other one. Notice that you can start and end with whatever, because I'm assuming that if A equals B, then that B equals A. I mean, that's kind of like a basic math thing, you know what I mean? If A equals B, then B equals A. Okay, cool. So you can start either way is fine. So my U and then my V's here. If I'm going to expand this, I got C1, U1, and then I have my V1 plus W1. C2, U2, V2 plus W2 plus all the way out. I'm going to distribute these guys into both of them. So C1, U1, V1. C1, U1, W1. C2, U2, V2, C2, U2, W2. And then I'm going to group them. These guys get grouped together. Those get grouped together. I might be going a little verbose here, as in like I'm writing too much when it's kind of obvious. And that's okay. I mean, you know, it's a flavor, I guess you can say. So I got my C1, U1, W1, C2, U2, W2. Notice that I put a plus sign right here. So I just got like one whole list plus another whole big list. And so I can say, well, I know what that list is. That is my U and my V together. And then I know what that list is right there. That's my U and my W. And there you go. Number 2 is done. Number 3. Yes, you have to do every single one of them if this is what's going on. So just as a reminder, that C somehow gets inside of there. So I'm going to start on this side, on the left side here. Put a C out in the front of a U1, V1, U2, V2, ... And of course, as you guessed, I'm going to go ahead and distribute that. So C, U1, V1, C, U2, V2. Notice that it's not C1, C2, C3. That was from the last one, not this one here, okay? Okay. I'm going to do the associative rule. Basically, I'm just putting some parentheses up here and saying, hey, these guys are grouped together. That's pretty simple. Like, why do you have to even do that step? Well, I mean, these are important because now you can see that my U's are grouped together, and then I got my V. So there you go. Number 4. It's a combo one, if you remember. There's 2 different things. First, I'm just going to start with the dot product. Whoa, it's not equal to 0 always. I'm saying it's greater than or equal to 0. So the dot product of these 2 guys is always greater than or equal to 0. Well, I'm going to definitely start with this guy. So if you don't mind, here we go. So VV. So then That would be C1. I think I maybe messed up this guy here. Yeah, I think I did. There's a C1 here and a C2 there. So this is... I guess you'd have to have a D there in the front. Okay, sorry. I messed this one up just a tiny bit because I forgot the C's in the front here. But it doesn't really change too much. I'm just putting this right here, and I'm going to put another C right here, let's say. That's great. So I'm just moving things around, C2. And then I got my D right there. And then we're good. Okay. That's really what's going on. Start with the D. See, now it looks like distance. I don't know. Whatever. Moving on. It's really not a big deal. So I got V1, V1, plus C2, V2, V2, plus dot, dot, dot. Okay, cool. Really, this is kind of interesting. I didn't know where to go from here, but I see that they're multiplied together, and so to simplify, couldn't I square it? And notice what happens. I already said way in the beginning that my CI is greater than 0, right? All my C's are greater than 0. So that's a positive, positive, positive. Well, this is positive, this is positive, this is positive. So I'm saying that they're always greater than or equal to 0 right there. Always, because you got squares. So there you go. That was pretty easy. Now remember that there's like a second part to this guy. How I wrote it is I said because my CI is always greater than 0, the only way to make my VV equal to 0 is when V equals the 0 vector. Okay, and then I'm finally done for all that. So notice again, I'm saying that these guys here are not going to make anything 0. How are you going to get any of this to be equal to 0 at all? And these are always positive, right? Literally every single V must equal 0. 0, 0, 0. And then you would add them all up to make it 0. That's the only way. And again, that just goes back to the number 4. There's like a postulate 2, I guess you can say, or something like that on that. I know I said that incorrectly. I'm just going to keep moving. So, next section. This is informal. 5.3. Orthonormal. Not orthogonal anymore. Orthonormal bases. Those are S's there. And then this also is talking about the Gram-Schmidt process. Schmidt process. This Gram-Schmidt process is on your quiz for sure. I don't know if it's on like an exam or something, but it's definitely on your quiz. And it's a little lengthy, so I'm going to do one with you, kind of show you around what's going on there, okay? But let's first talk about what this orthonormal basis stuff is. Bases? Okay. Anyways, when each set of vectors S subset of V, I think subset's going to have a less than or equal to sign. Anyways, no, it's a subspace, not a subset. It's a subspace. Okay, well, technical little things. Subspace, when S is a subspace of V, is orthogonal to one another. So each set of the vectors in S are orthogonal to one another, comma, then its S is orthonormal. Notice that the whole set is orthonormal. And what does this even mean? Like, what are you getting at here? Well, let me just make a really easy example. 1, 0, 0, 0, 1, 0, 0, 0, 1. If you were to draw these three, they're all orthogonal to one another. They're all 90 degrees from one another. So that was easy, right? I guess you can kind of say like your X, Y, Z kind of coordinate basis stuff. So that's orthonormal. Orthonormal sets are also linearly independent, and they form a basis for V. So this right here, like knowing that you have orthonormal, they're linearly independent, and also they form a basis for V. That's all from like the last chapter and stuff. The thing is that having linear independent and basis does not imply that you have an orthonormal set. So don't go backwards. I didn't want to really talk about it too much because the fear that it might go backwards or something like, oh, that stuff that we've already been doing, it's orthonormal. Not necessarily. So just watch out. Okay, let's do this Gram-Schmidt process. I'm going to show you the formula, and then I'm just going to do Gram-Schmidt like that, if that's okay. This is pretty long. What's going on is that we're trying to make an orthonormal basis given that we have an original B basis. So I got V1, V2, V3, so on and so forth. And then I want my B prime, so to be like W1. Let me try to write that just a tiny bit better. W1, W2, W3, ... Okay. So I have an original basis. I'm just going to call this the original. And I'm wanting to make an orthonormal basis from that. These right here will all be orthogonal to one another. They'll all be orthogonal to one another. Okay, that's kind of like the promise that Gram-Schmidt is giving you. So here's the formula. W1 is equal to V1. Cool. W2, it's like, what? That's so easy. Yeah, that's a good thing, okay? Is equal to V2 minus V2 W1. It's going to get really hairy. W1, 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 okay? Notice all the W1s. That's not V's there, okay? But there are two V2, V2 right there. W3 is equal to V3 minus V3 W1 divided by W1 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 minus V3 W2 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 W2, and it'll keep going as long as you need to. Obviously, it'll get much more complicated as you keep going. So I just want to show you some patterns to begin with, and then we'll get it on. Notice W1, 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 W1. Where do these guys come from? Right there, okay? And you repeat those same W1s right here as well, okay? When they say W2, they're meaning this guy right here comes like all the way over here to do all that stuff, okay? You're using the answer that you just got last time. Notice this is my answer. Now I'm going to also be using my answer over here all over the place. Okay? Cool. Let me pause this for just 1 second. All right. And so now let's actually do a Gram-Schmidt together. So here we go. Oops, wrong color. Sorry. 5, 3, 31. So Gram-Schmidt with my B equal to 4, negative 3, 0, 1, 2, 0, and then 0, 0, 4. Okay. So my B prime is what I'm looking for. I'm looking for, I guess you can call it W1, W2, and W3. That's my goal here. I need to find those three vectors. So W1, as you recall, is actually just the first vector. So 4, negative 3, 0. By the way, I don't know if you see this all the time, but I'm using these alligators to the inequality looking symbols to indicate a vector. These things could also be vertical and normally we use like square braces and stuff. Same thing. It's just, it's written horizontally rather than vertically. All the same when it comes to vector land here. Okay, so we got our first one. We're done. That's my answer. We're done there. Cool, huh? The second one, I now have to take the second vector, the 1, 2, 0, and I'm going to subtract from it that dot product. I'm sorry, the inner product. The dot product right here of this same vector here, okay? These are the same vector. But then with my W1, which was my answer from the original, which actually is the original in this particular case. So, my dot product with this guy and this guy. So 1, 4 plus 2, -3 plus 0, 0. And then divide that by the magnitude of W1 with W1. So you just repeat it twice. And then multiply that by W1, which is my 4, -3, 0. Phew. So notice the patterns. You see the patterns all over the place? Okay, that's just kind of something to kind of notice. Patterns are good. Let's go ahead and keep going here. I've got 4. Minus 6 is -2. It's got a -2 up there. And then all this down here, we got 16 minus 9. No, I'm sorry, plus 9. 2 negatives make a positive. Makes it 25. And then still times this 4, -3, 0. Distribute this. Subtract it from that. Blah, blah, blah. I got 33 over 25. 44 over 25, and then 0, of course. That's my second answer right there. W3, it's going to be a long one here, is that last vector, the 0, 0, 4, if you remember right here. But then I need to do that same subtraction business with each of these first and second answers here. So then 0 with the 4, I'm using this guy here. 0 with the -3, and then 4 with the 0. Interesting kind of stuff here. I don't know why I'm writing this one out so long. You could probably see what's going to happen here. And then times my answer I had right there. So there's one of them. The next one, again, I'm going to use my 0, 0, 4, but now with this answer here. 33 over 25, 44 over 25, and then that last 0 there. 33 over 25, 33 over 25, 44 over 25, 44 over 25, and then 0, 0. And all this is multiplied by, need a little bit more room there, 33 over 25, 44 over 25, 0. Okay, whew. Well, there's my answer. Ta-da. Well, notice here, 0 plus 0 plus 0 makes this whole thing go to 0. 0 plus 0 plus 0 makes the whole thing go 0. So all that just to say, that one was actually my answer to begin with. That does not always happen. You could have a whole ton of mess going on, but that's okay. This time, it was a little easier. 5-4. Math models and least squares. I'm just going to start it with math models. There's a least squares thing, but it's very small. So when they talk about least squares, I always think regression and stuff. And that's kind of what's going on here. They're wanting to find an x such that I guess you could say the magnitude or the distance here squared is minimized. Now we had, if you remember, I think it's chapter 2, where we had one of the questions on the quiz was that you needed to find a least squares regression line using a matrix A and all that stuff. And it was a big problem, and it had all these different formula things we had to do to make it work. Well, it's somewhat related to that. Again, let me just kind of remind you. You have all these dots, and you're trying to find a regression line, some best fit line for these guys. And you're trying to minimize the square distances, the vertical distances right here. So you want to take all these distances, you add them up, and you're trying to find the minimum of that. And we move on. So there we go. So orthogonal complement. This will turn up again and again here as we keep going. So that's S with a little perpendicular sign at the top here, is the set of all U vectors that are elements of the Rn, so they're vectors basically, U vectors, such that V dot U equals 0 for all V element of S. Okay, what does that mean? Because like that's a pretty cool little formula. What does it mean? I'm saying that my S orthogonal, S complement, orthogonal complement, I don't know, whatever you want to call it, S complement, is the set of all these U's. I mean, this is the basic right here. It's the set of all the U's, all my vectors. Okay, cool. Such that, given that in your regular S prime, S kind of thing, S complement, the regular S, all your V's there will give you dot products of 0. So they're always orthogonal to one another. So each U and V are orthogonal to one another, okay? For all of them. That's basically orthogonal complement. Cool. Direct sum. Direct sum. This is a pretty big explanation here, but let me just kind of give you the quick summary. We got Rn, it's all my vectors in Rn space here, could be said to be S1 direct sum with S2. Notice that's a circle with a plus sign between them, or a plus sign in the inside, okay? So it's a circle with a plus sign. Now, honestly, I've seen this kind of symbol used for other kind of things as you go on to different classes. Sometimes it's like a general operator symbol. They'll use other symbols kind of like this as well with a cross thing. It doesn't really have to mean something particularly here. I'm just saying that when you see this here in Chapter 5, they're meaning direct sum and all that stuff. So what does it mean? It's that it could be written this way as long as your x vectors could be written as S1 vectors plus S2 vectors. Notice this kind of direct correlation here. And that's for all x in Rn. What I'm getting at is this relates to these vectors, this relates to those vectors, and these relate to those vectors. If you can say that each vector in Rn is basically just you adding up some vectors from this guy and some vectors from that guy, then there you go. What gets interesting is if you had something kind of like this here. Notice that we're tying these two things in together. I'm saying that we had, I know I don't write my circle plus very well. But if you were to have some set and then it's orthogonal complement and you add them together, you basically should have every single style possible to make Rn. That's kind of my thought there, but we're going to not do that right now. I think that's part of a quiz or something. And I'll show you some other stuff as we keep going. So we also have then orthogonal subspace properties. So these are properties. Now there's some other things about orthogonal subspaces, but let me just give you these properties here just in case. The dimension of your S plus the dimension of your S, I want to say prime, S complement, should be equal to n, because again you're talking about Rn. Basically, again, I'm saying that all these plus all those should do a full set. So something similar to that. We got Rn is equal to, oh, I just said this a second ago. Guess I was thinking that. There you go. Whenever you have the complement, I'm sorry, I keep saying complement, but it's kind of that way. The orthogonal complement, yeah, that's fine. You do your direct sum between them, you get Rn. Cool. And if you complement, you get your original. So that's some properties for you. Let's do a proof. 5,445. So prove that if S1 and S2 are orthogonal subspaces, of Rn, comma, then their intersection consists only of the zero vector. Okay. Whew. So I have orthogonal subspaces here. Are they complements of one another? I think the key word that we're going to be looking for here is subspaces. Okay, subspaces is my key here. And why is that? Well, subspaces goes way back to, I think it might have been chapter 4, maybe earlier, where there's special properties that subspaces have. They have vector, yeah, I'm pretty sure chapter 4. Vector addition, closure under vector addition, closure under scalar multiplication. You have to have an additive identity and a multiplicative identity and all that kind of stuff. Cool. So I'm going to hang on with that. That's going to be kind of my starting point. And I'll show you why, because we're going to be talking about the zero vector mainly from the subspaces aspect. Okay, so let's go with that. I'm just going to lead right into it. Just let S1 and S2. Okay, cool. So by definition of a subspace of Rn, both S1 and S2 contain the zero vector. Now let's just pause on that. I said, subspaces. That's a pretty key word. Well, I know that they have to have the additive vector identity. So they've got to have that zero vector in there just because they said the word subspace. And so that's nice. Notice that we're already talking about the zero vector. So let me go back. That their intersection consists only of the zero vector. They both have the zero vector. That's a big check mark. We've got that done. But I need to prove that there's no other vector now that they're going to have together. Okay, so I'm saying they both have the zero vector, but I want to say that no other vectors are common. No other vectors are common. Okay, so let's keep going. By the definition of orthogonal subspaces, which is in the book, I don't think I listed it here, my V1 dot V2 should equal 0 for all V1 element of S1 and V2 element of S2. So if you go back in the book, they're going to talk about orthogonal subspaces. Basically, the vectors from S1 and S2 have all got to have, or they all got to be orthogonal to one another. They all got to have this dot product equal to 0 stuff, okay? So all of them have the dot product equal to 0. That's another definition, okay? Thus, V1 perpendicular to V2, I guess for all V1, V2, by the properties of dot products. Okay, so by properties of dot products. So that's going way back to the first section there. Notice that I'm kind of saying, look, I got this dot product equals 0. That means that they're perpendicular. Okay, that's what I'm saying here. By definition of perpendicular, look at all this by definition of this, by property of that. I thought it'd be pretty cool to do that in this particular case. So by the definition of perpendicular, I know that V1 cannot be parallel to V2, given some, I don't know, scalar. This is the fancy way of saying not parallel. Okay, not parallel. Those are scalar multiples of one another. They're not parallel to one another, but either way is fine. There you go. I cannot have any vectors that are similar to one another, not even the same, not even scalar multiples, not even if c equals 1. Like, c equals 1 is included in there, so you can't have them actually the same either, okay? No v1 and v2 are the same. Therefore, the only vector shared, is what I said, shared by S1 and S2 is the 0 vector. There you go. So they're orthogonal, their dot products are 0, therefore they're perpendicular, and therefore you don't have anything that's a scalar multiple or parallel one another. The end. Okay. 5.5. Applications. Been noticing they often do applications in the last section here. So I don't know why they put it down here finally, but we definitely need to talk about the cross product. You can't go through linear algebra without a cross product talk. So this shows up also in Calculus 3. I don't know if you've had Calculus 3 or not, but this is a very important topic, so here we go. U cross V is equal to, and this is my determinant method of doing it, which I never use, but I want to show you because it's a pretty succinct definition that you can't get wrong. U1, U2, U3, V1, V2, V3. Okay. Those are supposed to be determinants. This is a big determinant of a matrix. And so because you have determinants, I'm going to be using these guys as my cofactors. And so then I have my U1. I'm sorry. I'm using my I first, starting with my I. U2, U3, V2, V3. Trying to write it nice. I. But if you remember your signs, this is a positive, negative, positive always. U1, U3, V1, V3, J. And then plus, again, for my K side here we got U1, U2, V1, V2, K. I like to do capital Ks, that's why it's kind of confusing me. Okay, these are components. If you haven't seen the IJK components before, they don't have the little hats on them all the time. They sometimes just bold them. There is a difference between a vector. Let me just kind of make a specify here. A vector is not equal to a component. Now, you could say that this equals I, and if you did that, what you're basically saying is 1, 0, 0. That's fine, but these are not the same thing. This is a vector, like, 1, 2, 3. This is just I can't even write it. It's just a component. It's just that slot on a vector. It's just the slot, okay? So not the same equivalency. That way, I'm just telling you how I do it here because I don't have bolds. I can't bold my letters. I use little arrows for vectors, and I use little hats for components, okay? So if you do see this, they actually mean it's a vector with 1. It's a 1 in the front there. So you can technically write it like that, but they're not saying that they're actually the same thing, okay? That's just my little spiel. One more thing about these components, which I use very frequently, is the right-hand rule. I, J, K. And again, I just want to always specify that these are components. Always go counterclockwise. Counterclockwise. Okay, it's very important to go counterclockwise. Right-hand rule, because I can't show you my right hand, but basically when you put your, like if you take your fingers and you curl them in this way with your right hand, your thumb is sticking straight up out of the page towards your face. And that's, I guess, how you would specify it. And so counterclockwise is how your hand's doing it. Counterclockwise is how you're doing it here. Right-hand rule, more technically, is like you take these two vectors and you curl it, and there's your thumb. It sticks up that way, whatever. Counterclockwise. So, whenever I say, like, I cross J, it's going to be equal to K. Notice that I cross J equals a K. This guy, follow the path, this guy, okay? J cross K equals I. K cross I equals J. If you're going backwards, j cross I is a negative k because you're going backwards. Okay, so j cross I is a negative k because you're going backwards. These are very important. And lastly, like I cross I, you never really move it anywhere. You just come back to itself. Therefore, you get 0 out of that. Now, is that 0 vector? Or is that 0, scalar? Just it's 0. Okay. So that's my little talk about the components stuff. I'm going to be using this here on my way of doing a cross product. I know you're thinking, wow, this is a long video now. Well, we got to talk about it. So let me do my example for cross product now. I've got 1, 2, 3 cross 4, 5, 6. Now, I didn't actually talk about the symbol very much. Notice the cross means multiply, right? So we're multiplying two vectors. But see, when I'm multiplying these two vectors, I'm actually supposed to result in a vector. I'm going to result in a vector here, not a scalar. If it were to be a dot product, remember how we already talked about that earlier. If you did a dot product, this results in a scalar. Okay, so that's a scalar dot product. Cross product results in a vector, but they both mean multiply. That's why we have to differentiate it some other way. Okay, cool. So we're going to get a vector out of this whole thing. What I do, this is my manual way. I'm not going to do this component, or I'm not going to do that determinant method up there. I can't do that. But I do like to do this method here. I like to call it the FOIL method. But that's not, don't call it the FOIL method. It's just, that's what I kind of think of it. It's like expansion. Expanding is what I really should say. Always start with a 0, because I cross I is 0. 1 times 5, that's an I cross j, should be a k, and that's a positive k. Keep going. 1 times the 6, and then again, that's I cross k is going to be a negative j. Okay. 2 times the 4, again, that's j cross I is going to be a negative k. I'll show you some patterns here in a second. Always a 0 in the middle. And then you got a 2 times the 6, and then that's j cross k is a positive I. Okay, all these are components. 3 times the 4, and that's going to be a positive j this time. And then I got 3 times the 5, and that's going to be a negative I. And then I got a 0. So notice zeros in the diagonal, okay? Also notice how I was doing this. This 1 goes here, here, and then here. Okay? Say I got my 2. Goes here, here, and here. All right, lastly, I got my 3. Goes here, here, and here. Okay? And again, zeros in the diagonal, so always get that. Notice again, k, negative j, j, I, negative I. Kind of like opposites of one another. It's like a 3 by 3. You got your 0, your k, your negative j, your negative k, 0, positive I, positive j, negative I, and then 0 again. So that's kind of like a matrix setup for it. Notice again, they're opposites of one another. J and j, k and k, I and I. It's kind of like they're mirror images in a way. Okay, so that's how I kind of remember it. Anyways, so you can try to simplify all this, but remember that you're going to have your I components together, your j components together, and your k components together, just combining like terms. So your i's, I have a 12 minus, notice the negative right there, minus the 15. My j's, I got a negative 6 plus the 12. And then for my k's, I've got a 5 minus 8. Put it all together. Negative 3, positive 6, negative 3. It's a classic example. And all that was just an example. It wasn't actually the problem we're going to be doing. But I wanted to show you a cross product for sure, in case you hadn't seen it. Again, if you do this in Calculus 3, I know you're doing this in Calculus 3. I'm just saying, if you have taken Calculus 3, then it's no problem. Otherwise, there you go. So properties of cross products and stuff, I'm not going to list them all, but we got u cross v is equal to a negative v cross u. Okay, so that's pretty interesting. Notice that they're not commutative. Cross products is not commutative. You can't flip them. Like, 1 times 2 is not 2 times 1 kind of thing. But it is similar. It's just a little different there, okay? U cross U is equal to the 0 vector. Notice that, again, you're not going anywhere with it. Again, that's a vector. Make sure you put that as a vector here. U dot V cross W is equal to U cross V times, or dot, the W. Now, I don't know what you would call this. Kind of like distributive, maybe? I don't know. This is kind of a weird little formula, but it works, so they say it's cool. We're going to say it's cool. Okay. U cross V perpendicular to W and U cross V perpendicular. Why did I have a V there? Oh, never mind. I wrote it wrong. Sorry, back up. Sorry. U cross V is perpendicular to U, and that's the worst little U in the whole wide world. There you go. Now it makes more sense. And U cross V is perpendicular to V. What they're trying to say here is that when you cross product two different vectors, you get a third vector. Classic example here. You got your U, you got your V. Cool. Perpendicular to both of them would be a W. Okay. But that W is perpendicular to this one, and it's perpendicular to that one. I don't think that these two have necessarily need to be perpendicular to start all that, but definitely for sure this result is perpendicular to the other two guys, for sure. So that's what they're trying to say there. The magnitude, the distance, the length of U cross V is equal to magnitude of U, magnitude of V times the sine of theta. This is actually related to area. They relate this to the area of a parallelogram, I believe. And so, I think so. And so they're talking about like area of a triangle and all that kind of stuff as well. I'm not going to get into that. We got U is parallel to V, of all the vertical line symbols we use. So U is parallel to V if and only if that U cross V is equal to the 0 vector. Now that right there means parallel. I know we've got like tons of these vertical lines. Why do I just mix it up even more? So we got U is parallel to V if and only if U cross V is equal to 0. Notice the if and only if means that you're going back and forth. If you have this, you can get that. If you have that, you can get this. So that's kind of handy. And 5565, I'm going to say prove that last property. This guy right here. Prove that. So let me just rewrite it in English. U and V are parallel if and only if U cross V is equal to the 0 vector. Okay. Because it's if and only if, you must do two different directions. Now, my proof here is going to be kind of cheesily short, but that's fine. It's no big deal. As long as you're doing two of them. You can't just do one. It's not a typo. You can't just do one and call it a day. This is two for sure. So I'm going to say, number one, let U be parallel to V. Okay? Thus, because they're parallel, I could say that my V vector is a scalar multiple of U. Okay, what I'm getting at is you can rewrite my V as a scalar multiple, even with a 1 in there is fine, of U. So they're kind of related to one another in that regard. Therefore, if I had U cross V, what I'm really saying then is U cross CU, right? Now there's a property with this cross product stuff that you can take the C and move it out. And so then I got a C U cross U. And that definitely is equal to C times 0 vector. And C times 0 vector is definitely still the 0 vector. Cool. So we're done with that one. Number 2, now we're going to have to go the other way. So now let U cross V equal the 0 vector. and then we have to go and find that they're parallel. And so most often, if these are simple proofs for if and only if, you're basically just going in reverse. Often that's what's going to happen. So I'm thinking about that as we're going here. I'm saying thus either v is equal to 0 vector, or v is equal to cu for some scalar multiple. Okay, so I'm saying that, okay, we have a cross product is equal to 0 vector. Okay, either one of them is equal to 0, u or v is equal to 0 vector, so either one of them is equal to 0, that makes the whole thing 0, that makes sense. Or I can have them parallel. Again, I don't want to say the word parallel yet, but you get the idea. I'm saying that there's a scalar multiple of one another, and therefore you're going to result in what we just had right here. Basically, I'm kind of skipping from like to this step right there. That's what I'm kind of doing. Now, this right here, I wanted to include because this is the trivial solution. It's still important to include these because I don't see a trivial solution going this way necessarily unless c equals 0. I guess you could say c not equal to 0 or something. I don't know. That doesn't matter as much in that regard. Here, though, I found it important, so I go ahead and include it just because it made sense to me. So that's a trivial solution. So aside from the trivial solution, like I'm actually saying that in my proof here, just to remind us, of v equal to 0 vector, I'm going to assume that v is equal to cu instead, okay? Cool. Well, if I have that, that means they're parallel, so that means they are parallel, and you're done. So, I don't know. Therefore, u parallel with v, I guess. And now we're done for sure. Okay, done with this recording. Cool. If you have any questions, let me know. Thank you very much. Have a great day.